Okay, so in the last video, we interpreted what the empirical rule was and said if we're one standard deviation above or below the mean, that will include 68% of all observations. Two standard deviations, 95, three, 99.7% of all observation. That's a lot, right? So let's look then and see how we can. Let me give you an example of a definitive case where there's a mean and a standard deviation, and then we'll interpret what those results mean. So let's go ahead and make another normal distribution curve. And with the normal distribution curve, you'll notice, number one, symmetry, right? We're not skewed heavily towards one side or the other. And there's a certain degree of height to it so that, again, both sides, if I were to draw the mean down the middle, both sides are equal, comprising 50% on one side, 50% on the other side. So I'm going to use an example of the IQ test scores. Some people have taken the intelligent quotient test when they were younger. They got some results. It was hard to interpret what those results meant. But if you put it in the context, and this is what they do, you put it in the context of statistics and means and standard deviation, you know exactly where you stand with those scores. So again, mu is going to equal the mean or the average of all the data points we have. And we've been collecting data points on IQ scores since the early 1900s. So we have a lot. We have a population, right, of test scores. Hundreds of thousands, if not millions of test scores. So based on all of those scores, we know that the average IQ score is 100. So we can even put that right down here. That 100 is the average score on the IQ test. We also know, based on all those observations, thousands and millions of observations, that the population standard deviation is 15. Okay, so let's go ahead and we'll graph that out. Here's one standard deviation above, one standard deviation below. My drawing's a little off. They're equal on both sides, trust me. So this is one standard deviation below. One standard deviation equals 15. So if we take one below the mean, this number out here is 85. 100 minus 15 is 85. If we go one standard deviation above the mean, we have 115. Okay, so now we have actual scores to look at and use in our examples. So what do we know? We know this entire area, this entire region here, if we were to shade it in, accounts for 68% of all of our observations. Now just take a moment here, because sometimes students get confused with this. That stands to reason that since these are equal, they're symmetrical, that this area here equals 34%, and this area here equals 34%, right? Because the whole thing equals 68%. It's divided equally down the middle, so 34 and 34. Okay, so based on that, let's ask a question. Let's say I scored a 115 on the IQ test, and I want to know how many people did I score better than. This could be anything. Any normally distributed data will tell you this. Height, shoe size, test score, anything that has a normal distribution follows this empirical rule. So that's what I find so fascinating about this information. So if we have a normally distributed distribution curve and a bunch of observation points, we could really start to answer some questions. So I scored a 115. I want to know how many people I scored better than. Well, that's going to be the area. Here's 115 exactly, right? So that's the area under the curve from this point back. So all of this area, if we were to shade from here back all the way to the end of this curve. So imagine all this area is shaded right here. That's the percentage of the population or the proportion of the population that I scored better than. Well, okay, we know from here to the midpoint is 34%, right? We know that, right? Because we did that with the empirical rule. We also know from the midpoint all the way back to the end of the curve this way is 50%, or half of the curve. So I know that if I scored a 115 on the IQ test, I scored better than 84% of the people who took that test. Okay, very good, right? Excellent. And you could figure out anything as you move along here, right? If you scored an 85, you would say, well, how many people did I score better than with an 85? Well, that requires a little more math, right? Because we know the 34% here, but we also know this entire area on this side is 50%. So if I take 50 and I subtract 34 this time from it, I'm going to get 16%. So if I scored an 85, I only scored better than 16% of the people that took the score. And so on. You could find any point along here, 86, 87, 88, 89. We need some special statistics to do that, to make it easier for us, because we don't want to use big, massive formulas to figure out if I scored an 86, 87, 88, 89. But if it's one standard deviation, one complete, perfect standard deviation, I could use the empirical rule to figure out how many people I scored better than, right? Makes it a lot easier. Let's do 2 standard deviations. So if I go out 2 standard deviations, now 15 minus 85 is 70, right? And 15 added to 115 is 130. I could also do I know 2 standard deviations is 30, right? Because 1 is 15. So I can do 100 minus 30, or I could do 100 plus 30, and I get out to where two standard deviations on the nose, right? Not 2.1, 2.2, 2.3. Exactly 2 standard deviation leaves me at 70 and 130. And we know that, based on the empirical rule, 95% of all observations will be between 2 standard deviations below and 2 standard deviations above the mean. Okay, now it can kind of get a little interesting. Number one, because I might have to do some math here. But so that leaves me with an area here from this to this of 47% of the curve, right, is under that 47.5, 47.5% of the curve is from the midpoint to the 2 standard deviation mark. In the same way here, we have 47.5% of the curve, because 47.5 and 47.5 is 95, right? I hope I have that right. I'm doing the math in my head here. So let's go ahead and use the same example. I scored a 130, right? That's kind of the genius mark, I think. But I scored a 130 on the IQ test. How many people did I score better than? Okay, well, we have 47.5 just on this side of the curve. And then we know this other side of the curve is 50%. So I scored better than 97.5, almost 98% of the people I scored better than if I scored a 130, which is 2 standard deviations above the mean. Okay. Again, digest some of this, because it might even sound crazy, but again, this is one of those things that I learned that I was just like, wow, this has to be able to help in decision making and problem solving and everything else, because we can look at normally distributed data and really make some good inferences. If we go out one more, we're talking 55 down here, 145 up here. That's 99.7% of all observations under the curve. So again, if I wanted to say how many did I score higher than here, if I'm at 145, I break that 99.7 in half, add it to the 50% on this side of the curve, and I could predict how many people, or I could not predict, I could tell you how many people I scored better than. And again, any normally distributed data that takes this bell-shaped curve will tell you you'll be able to make a lot of inferences from that data. And again, we don't necessarily, we don't need to always have the population mean and the population standard deviation. It holds true for the sample mean and the sample standard deviation. The shape of the curve is a little different because we're not dealing with a population, we're dealing with a sample size. So the shape of the curve is going to be a little different. We learned that the formula is a little different for the sample standard deviation, but everything that it's telling us is going to be the same. Now, as we move forward, we're going to find out not everything falls in the neat little box of 1 standard deviation, 2 standard deviations, 3 standard deviations on the nose. It's going to be a little different. We might score a 92 on the IQ test score. Now it doesn't fall into that neat box of 1 standard deviation. We have to use some other mechanisms, some other mechanics to really start to understand now what's the proportion on either side of that if we're going to, again, not fall specifically on a standard deviation. And we'll be doing that in probably next week's statistics video lectures to start introducing a T curve and a Z curve to you so we could standardize these standard deviations. That sounds like a mouthful. Standardize the standard deviation and really understand where we are with any number, any observation that we get so we can interpret it under the same kind of rules that we have here.